or the
Yes.
memo of the test?
Tonight's session.
Yes, we did, sir. For
All
ID.
right, good. Uh, can you guys see my shared screen?
Yes, sir, we can
Yes, we
see
can.
it.
Okay, just want to check something quickly. Bum, bum. Mhm, mhm, bum. All right. So, as per the memo I sent in the group, we'll first look at dynamics. All right. We'll look at, I believe, 3 or 4 exercises on dynamics, take questions, then move on to hydraulics, as per the memo. All right. Um, Now, we first are going to look at this question on dynamics. Right? It's one of the questions that is in the exercises that I sent you guys. Right? There was quite a few exercises that I sent you on dynamics. Right? I don't remember the page, but this is just, in fact, all the four. What is this? All the four, or at least 3 of the 4 exercises we are going to do are part of those exercises that I sent you. Right? The fourth one, I think, is not right in the handouts I sent you. All right, without further ado, let us look at these questions. So question 3.1, define Newton's first law of motion. So this one we're not going to write down. I'm just going to ask one of you to define Newton's first law of motion in a way that you understand Newton's first law of motion. Anyone, quickly.
Uh, the way I understand it, so an object at rest will remain at rest unless an external force is being acted on it. And if it is in, how can I say, if it is in motion already, it will stay in that consistent motion
Mhm.
until an external force is being acted on it.
Wonderful. All right, that's the understanding around Newton's first law of motion. I would say the most easiest way of defining or stating Newton's first law of motion is as follows. Right, you can say that Newton's first law of motion states that a body in a body at rest and or a body in uniform motion will preserve its state of motion unless an external force acts upon it. That's the most easiest way because it incorporates essentially both scenarios where the body is at rest and or when the body is in uniform motion. All right. Now let's look at 3.2. Right. 3.2. Motor car is traveling at or is traveling on a horizontal road at a velocity of 54 kilometers per hour. The mass of the motor car is 750 kilograms and the resistance to motion is 300 newtons. Motor car stops over a distance of 35 meters when the brakes are applied. All right. So let's draw before we get to the question. It's because we've been given enough information. Let us draw the free body diagram. All right. The one thing we can take away from this is that the object is moving on a horizontal surface. Right. So they say the motor car is traveling on a horizontal road. All right. So say this is the motor car. Right. It's traveling on a horizontal road. So the surface in which it is traveling on is horizontal. Right. Right. Now let us show all the forces that are acting on this. All right. At first, all right, all the forces we are going to look at from the perspective of the Cartesian plane. All right, that's our Cartesian plane. All right, because our surface is horizontal, the x-axis are parallel with the horizontal plane, and the y-axis, right, are as follows here. So because we are looking at an object that's moving on a horizontal plane, right? The Cartesian plane, essentially, you draw as follows, right? Either way, though, the most important thing as far as the Cartesian plane is that you draw the Cartesian plane with reference to the surface in which the object is moving. Right? So if the surface is such that it is at an incline, right? So you draw the Cartesian plane relative to the inclined plane. If the plane is horizontal, then you draw the Cartesian plane relative to the horizontal plane.
Showing the example?
Just make sure you've muted yourselves there. Ne? Right. So of course, we know we have the normal force acting in this direction. Then we have the weight acting in this direction. Let's make this orange because it has to do with the object. So we have the weight here. The weight we know is equal to mg. Right. Offsetting mg is the normal force. Right. And then let's say this is moving in this direction. Right. So this is moving in a positive direction. Right. But because we are looking at part of the motion where the object is now braking. Right. The most important thing here to understand is that when an object brakes, it does not change its direction of motion. Right. What changes is the direction of acceleration. So assuming that this object is moving towards, say, east, right, it means our acceleration will be pointing in this direction, right? Because now this is decelerating, right? If it was accelerating, the acceleration would be in the same direction as the motion, but because it's decelerating, right, our acceleration is going to oppose the direction of motion. Are we in agreement here before we move on?
Yes, sir.
Right. So that's the direction of acceleration. What else have we been given? So before we look at what else we've been given, right, another force here would be the frictional force, right? If this is headed in that direction, friction always opposes the direction of motion, right? And they said here the resistance to motion is 300. So Fr is equal to 300 newtons. Right? These are the forces that we've been given essentially, right? This one and this one, right? They don't necessarily have to give us, right? As long as there is an object on a surface, these two you get automatically, right? As soon as you have an object on a surface, you get the weight and you get the normal force, right? Now, which other force do we have here, right? That force hasn't been given to us, but based on the scenario, there is a force that we have left out here. Which force is that?
Braking force, sir.
Yes. So the braking force. Now, to understand how you look at a braking force, the braking force is always in the same direction as the acceleration. Or let me say, the force being applied, right? Be it the force that is being applied for the objects to accelerate, that force we take as Ft, total force applied. When the object is braking, the force applied is named as the braking force, which is Fb, right? So both forces are applied forces. This one we get when the object is accelerating. This one we get when the object is decelerating, right? The most important thing to take note of here is that the applied force is always in the direction of acceleration. Are we clear here? Hello?
Yes, we are, sir.
Yes.
Right.
sir.
So these are all the forces that are acting on this object, or these are all the forces that this object is being subjected to, right? Now, after having drawn your free body diagram, you are able to get the vector sum of forces, right? Now, how do you get the vector sum of forces? Right, the forces that are going in the same direction as acceleration, you take as being positive. Forces going against acceleration, you take as being negative. So we have two forces. Now, when looking at the forces of the vector sum thereof, we look at the forces that are parallel to the axis where the work done is taking place, right? So the work done is taking place along the x-axis, right? There is no work done taking place along the y-axis, right? Because both of these forces cancel each other out, right? So essentially, work done is only happening along the x-axis. So we look at the forces as far as the vector sum of forces. We look at the forces involved, right, for work done taking place, right? So our vector sum of forces going in the same direction as acceleration are going to be positive, right? So forces going in the same direction as acceleration here is Fr and Fb, which means F net is equal to Fb plus Fr, right? There is no force going against acceleration, meaning that F net is equal to this here. Any questions? No questions. Wonderful. Now, what else have we been given? They said, so that is as far as the free body diagram. Now let's look at what else we've been given that we can use, right, in the subsequent questions. We've been given the velocity. Now the velocity is 54 kilometers per hour. Is that the initial velocity or is that the final velocity?
Initial, sir.
Right, so we have the initial velocity. Initial velocity is 54 kilometers per hour. Right, this you have to convert to meters per second. Converting to meters per second, you divide this by 3,6. What is 54 divided by 3,6?
15, sir.
So this is 15 meters per second, right? Do we understand?
15.
Do you understand how we get the 3,6 divided by 3,6? Yes, no?
Yes.
Yes, sir.
Yes.
All right, good.
Yes.
All right. We also have the mass of the motor car. So the mass is 750 kilograms. Resistance is 300. Motor car stops, right? So they tell us that the motor stops over a distance of 35 meters when the brakes are applied. So essentially, we get two things from that statement, right? If the car stops, it means we also have the final velocity, which is equal to what?
0.
So that's 0 meters
Zero.
per second. And we are also given the displacement of the car from when the brakes are applied to when it stops, which is 35 meters. Right, so that's all the information we've been given here. Right, now let's look at 3.2.1. Calculate the following, the deceleration. Right, they want us to calculate the deceleration. As far as deceleration, you've been given the initial velocity, you've been given the final velocity, and you also have the displacement. Right, so you can simply use the kinematic equations or equations of motion. It's the simplest one to use here based on what we've been given is v squared is equal to u squared plus 2as. Right? We have v, we have u, we have s. So we solve for a. Solving for a, A will be equal to v squared minus u squared divided by 2s. Right, this is equal to final velocity is 0, so that's 0 squared minus initial velocity is 15 squared divided by 2, s is 35. What do you get here?
Minus 0.214.
214 meters per
Sorry,
second.
same man, minus 3.214.
3 points. Are we all getting the same here?
Minus 3.214.
Is everyone getting the same thing?
Yes, sir.
Yes, sir.
Right. So this is one approach you can take. Right. If you've taken this approach, then you say, yeah, therefore deceleration is equal to 3,214 meters per second squared. Right. But you do not leave your answers as just negative. Right. The fact that this is negative is based on the approach we took. Right. Based on the approach we took, right, we are getting negative because if this is deceleration, then it means it is headed in the negative direction. Right. That is what this stipulates. That this here is deceleration, hence the negative. Right. Otherwise, there is no such thing as a negative acceleration. The acceleration tells us of the direction of acceleration. So if it was positive, right, based on this approach, so using this approach, if it was positive, then it would have been acceleration. But because we are looking for deceleration, or because the object is decelerating, that is why our answer here is negative. By that, I mean, right, by approach, I mean you could have taken this approach instead. Right, you could have said v squared is equal to u squared, and then taken into consideration that this here represents deceleration. So instead of adding, you subtract. Right, you say minus 2as. Right, the minus is telling us that this here is deceleration. Right, and then when calculating your acceleration, would have been a is equal to u squared minus v squared divided by 2s. Initial velocity is 15 squared minus final, which is 0, divided by 2 into 35, right, which would be equal to same in magnitude, but now it will be positive 3,214 meters per second every second, right? So this one is positive because of what? Of the approach we took. Either way, though, the final answer, you must make certain that it is positive, right? Based on this approach, right, you've already accounted for the fact that this here is deceleration, right? That is why the answer we get is positive. Whereas with this approach, we didn't account for the fact that this here is deceleration, right? The answer essentially told us that this, in fact, is deceleration, right? Both approaches are fine as long as you understand what to do when using whichever approach. Are we clear?
Yes.
Yes, sir.
Right? It is important that you do not leave your answers as negative. Why? Because it might prompt you to make a mistake here. Remember, when accounting for the vector sum of forces, we have already considered what that direction of acceleration. The fact that F net is equal to FB plus FR, that is because we looked at the direction of the forces relative to the direction of acceleration. So in that sense, in this equation, we've already accounted for acceleration. Hence, if ever you have to use the formula F net is equal to ma, right? You do not substitute your acceleration as negative here. Why? Because on your free body diagram, you've already accounted for the acceleration being negative. So if you substitute your A here as negative, it will be like you're doing it for the second time. It will be like you're doing it twice, which is wrong. Do you feel what I'm saying here?
100%.
All right. Right. So those are the two approaches you can take for 3.2.1 in calculating deceleration. Right. 3.2.2 calculate the braking force. All right, 3.2.2, they want us to calculate the braking force. All right. Now, if you look at our vector sum of forces, right, we have FR, and essentially we have MA because we have the mass and we have the acceleration now. So you can simply use this, right, using the formula for the vector sum of forces, which is based on our free body diagram. All right, at this point, you've already established that F net is equal to FP plus FR. All right, so solving for FB here, F net we know is equal to MA. This is what we are looking for, and we have FR. All right, so making FB the subject, all right, FB will be equal to, so we transpose FR to that side, meaning on this side you'll have MA and then FR becomes negative. All right, our mass is 750, yes. So the mass is 750. Acceleration we've just calculated, and it's 3,214 minus FR, which is 300 newtons. Yes, it's 300 newtons. And what do we get here as FB? If the assumption that FB is going in the direction or in the same direction as acceleration, if that is correct, the answer you get here must be positive. If it's negative, it is still correct, but it just means that the direction of FB on our free body diagram is incorrect. So what are we getting here?
211
211
0.5.
0.5 newtons. Right? Are we getting the same thing here?
Yes.
Right. So there is absolutely no number after the 5 here.
Yes.
I know, sir.
Okay. Right. The fact that this is positive means that the assumption for the direction of FB is correct. Any questions on this one? No questions. Wonderful. Right. Let's look at 3.3 now. (3.3) A train starts from rest on the top of a 2% incline and runs 1 kilometer down the incline under the force due to gravity only. The resistance against motion is constant at 60 newtons per ton. Right, let's draw the free body diagram. So we have a train, it starts from rest at the top of a 2% incline and runs 1 kilometer down the incline under the force due to gravity only. All right, so this is at an incline. Right, so you have an incline. Right. They said the object is at the top of the incline. Right. So we have an object is at the top of an incline. So we know we have the number of force there. And then we have the component of the gravitational force. It is perpendicular to the plane. Right, that one is Fg perpendicular, which is equal to mg cos theta. And then we have the component of the gravitational force that's parallel to the plane. That one we denote as Fg parallel, which is mg sine theta. And then, of course, here we have the normal force. Right, now let's see what else we have here.
Sir,
Yes.
I just have a question, sir. So if the object, sir, is going down because of gravity, doesn't that mean that the Fg will be on the opposite side?
The
The Fg, the gravity force that is parallel, doesn't that mean that will be on the opposite side
nope.
because
So
it opposes motion, sir?
no. You mean this here, Fg?
Yes, yes. It opposes
Fg.
because the object is running down.
So Fg doesn't oppose motion for objects
Okay.
that are on an incline. Right. In fact,
Okay.
so the forces that I've drawn here, these are the forces that this object is being subjected to even before it moves. If you understand what I mean here. Right. So meaning
Yes, sir.
the components of the weight are going to be in the same direction regardless of the direction of motion. Do you get that? Remember,
Okay, sir.
your weight is always acting in this direction. Right? Always perpendicular to the ground. Always. Right? So in that direction. Right? That is why its components will always, right? You'll always get one that is parallel to the plane and one that is perpendicular to the plane. That is because the weight, regardless of the direction of motion, is going to be acting in the same direction, perpendicular to the ground every time. Right? So the components of Fg are always going to be in the same direction, regardless of if this object is moving down the plane or going up the plane. Right? In fact, in this case, they even said that and runs 1 kilometer down the incline under the force due to gravity only. Right? That is to say that there is no force applied here.
I understand now, yes, sir.
The
I
Fg,
understand.
the component of the weight that is in the direction where the work is being done, is enough to pull this object down the incline. You see that, yeah? The force that opposes motion is FR. So FR here, seeing that this is moving down the incline, it means FR will be in the opposite direction. So we have FR in this direction. Right, FR, which is equal to the resistance against motion is constant at 60 newtons per ton. 60 newtons per ton, right? Now our mass is typically in kilograms, right? But let us write this as 60 newtons per ton for now, right? That's our FR. Now, direction of acceleration. Right, direction of acceleration is going in this direction. Now, as far as our free body diagram, are we in agreement here? Your free body diagram essentially tells you half the problem, or it solves for you half the problem. Right? If you get this right, it is likely that you are going to get the subsequent questions on this correctly as well, because they'll be based on your free body diagram. For your solution, they'll also be based on your free body diagram. So again, are we in agreement here?
Yes, sir.
Yes,
Right.
sir.
Okay. So that's our free body diagram. Question is calculate the velocity of the train at the foot of the incline after 1 kilometer by making use of the law of conservation of energy. All right, hint, the mass, let the mass of the train be m kg, right? So as per the hint here, we are going to take the magnitude of the mass of the train as m kgs, right? So as far as what you've been given, right, aside from those forces that the train is being subjected to, we also have, so we have S, which is 1 kilometer. So S is equal to 1 kilometer is 1,000 meters, essentially of the mass of the train, which is m kg, right? So the m stands for the magnitude here. Are you guys following?
Yes, sir.
Right. So the m is in mkg. They want us to calculate the velocity of the train at the foot of the incline, right? So essentially, you have the top of the incline. They want us to calculate the velocity of the train at the bottom of the incline. So the 1,000 kilometers, the 1,000 meters is from essentially the top of the incline to the bottom of the incline. All right, you'll simply just call it the velocity at the bottom. That is what we are looking for. All right, they gave us essentially the ratio of incline. Right? If they've given you the percentage of the incline, they've inadvertently given you the ratio of the incline. So if it's 2%, it means the ratio of incline is equal to what? What is 2%?
1/50.
Second?
1/50. 1 to 50 or 1/50.
All right. So for those that don't get it, this is, so 2%. What is 2% equal to? It's 2/100, right?
Yes, sir.
Yes.
0.02.
Percent, right? Which is equal to 1/50, right? But in decimal form, right? In fact, you don't really need to write it in decimal form. So you can write it as 2 over 100, or you can write it as 1 over 50. That's the same thing. Or you can write it as 0.02. Right? How you are going to use it is going to give you the same thing anyway. Right? But what you need to understand from this is that if you've been given the percentage of incline, they've essentially given you the ratio of incline. Right? Now you use the ratio of incline is you simply use tan theta is equal to the ratio. Right? Tan theta is equal to the ratio of incline. Right? So essentially, tan theta is equal to, so here you can use 2 over 100, or 1 over 50, or 0.02. And then to get theta, it will be equal to arctan of 2 over 100, or 1 over 50, or 0.02, which will give you the same thing. So what is this equal to?
One comma 546.
146 degrees. So it's 1,146 degrees.
Yes.
Right, so that's the angle of incline. Right, so we're looking for V at the bottom, and they were specific as to the approach you should take here. Right, so you don't just use any approach. They were specific. They said by making use of the law of conservation of energy. Right, now as far as the law of conservation of energy, right, before we get to it, let us first express our FR in terms of just newtons. Right, the FR we've been given is in terms of newtons per ton. Right, we are going to change that, right, to be expressed in terms of just newtons. Right, so FR is 60 newtons per ton. Right, so the first thing we're going to do is convert the ton to kilograms. Right, 1 ton is equal to 1,000 kilograms. So essentially, ton is 1,000 kilograms. Right, and then to get rid of the kgs, you simply multiply this by your mass, and the mass here is m kgs. Right, and then of course this and that cancels, therefore meaning FR is going to be equal to 60 divided by 1,000 times m. Now what is 60 divided by 1,000? So I am getting here so this
0.06.
0.06. Right, now remember here the magnitude of the mass is m, so this times the magnitude of the mass, right, is what? Is m. So this essentially is going to be 0.06 m newtons. Right, I'll see you together here.
Yeah. Say we are together, but hey, I'm a bit confused.
Why are you confused?
Can you repeat that one again? Can you repeat that one? I understand when I thought maybe you just multiply 60 times 1,000. Because I thought we are going to multiply 60 Newton times 1,000 kg,
Thousand.
because 1 ton is equal to 1,000 kg.
Yeah, but remember the ton here is the thing. It's per ton. If the ton, it's per ton. Right. So the 1,000 is converting the ton to kilograms. Remember that one
Okay. I got you say now.
is equal to 1,000 kilograms. So all you are doing is converting
Yeah.
this from this to that. Right? Bearing in
Okay.
mind that here it is a denominator. Are you with me now?
Yeah. Yeah, I'm with you, sir.
Right. And then, like I said, right, as per the hint, they said the magnitude of M, the magnitude of the mass is M. Right. So we are going to express the magnitude as just M. So taking that into account, it means if you multiply all of this, it is going to be 0.06 M newtons. Right. So whatever the magnitude
sir.
of M is, right, FR is going to be equal to 0.06 M newtons. Are we together here?
I got you now, sir.
All right. So that's the magnitude of FR essentially. Right. Now we can apply the law of conservation of energy. Now, who can state the law of conservation of energy for us? If you've been asked to state the law of conservation of energy, how would you state that law?
Energy can't be created, neither can it be destroyed. However, it can change from one form to another.
Perfect, 100%. Right. So there's the way that we state it in words, and there's a way that we express it mathematically. Right, which is what they want us to do here. That is not to say that there isn't a different approach that you can take. There is, but because they've specified for the students to use the conservation of energy, then that is exactly what you must use. Right? There's this thing. Right. So as far as the law of conservation of energy, right, this is how we express it mathematically. Right? Take note here that if the body we are looking at is accelerating, then this is how we express the conservation of energy. Right? We say the total work done plus the potential energy at the first point plus the kinetic energy at the first point is equal to the potential energy at the second point plus kinetic energy at the second point plus the work done to overcome friction. Right? This is how we express it when a body is accelerating. When the body is decelerating, right, the work done here still represents the work done or the total work done, right? But because this is breaking now, right, we say the total work done for braking to take place plus EP1 plus EK1 is equal to EP2 plus EK2 plus the work done to overcome frictional resistance. Right. Now the object here is accelerating. So this is how we are going to express our law of conservation of energy. Right. And then you take things from here. Right. Just to break down the law of conservation of energy, right, it's simply based on, right, the energy of the object between 2 points or between any 2 points in the object's motion, right? So the 2 points we're looking at right now is the point at the top and the point at the bottom, right? Now we look at the energies involved, right, for the object at the top, right? Now the energies that could be involved here, the two obvious ones, right, are based on mechanical energy, right? We know we have a kinetic energy here, and you also have potential energy. And then sometimes, by sometimes, I mean when the object or when there is a force that is applied for the object to accelerate, right, then there is going to be some work done due to that force. And as you should know by now, is that work done is a form of energy, right? Hence, the standard unit of measurement for work done being joules. Right? And then when the object moves from this point to any other point, right, in the object's motion, there is going to be some work done to overcome friction. There is, of course, if there is some considerable friction, right, between the two surfaces in contact, right? Because you do get cases where they say that the object is moving down the incline freely, which suggests that there is little to no friction. Either way, in that case, we say that the friction is so small that it is negligible, so we neglect friction. Right? But as far as the law of conservation of energy, right, we express it the way we do because of what I've just explained. That if you're considering friction, then when this moves from this point, right, to anywhere, right, along the object's motion, there is going to be some friction or some work done towards overcoming friction. Right? In this case, we're just looking at the top and the bottom. So by the time that this object gets to the bottom, there will be work done to overcome the friction. Right? And then at the bottom, you also have the kinetic energy that was built, right, from when the object moved from the top to the bottom, and also the potential energy, right, at the bottom. That is where this comes from. Are we clear here? Right, I'm explaining that because I don't want to hear people saying they forgot how to express this. If you forget how to express it, then look at it practically in terms of all the energies involved. When an object moves from point A to point B. Right? This applies to whether the object is on a slope or a horizontal plane. Any questions on this one? No questions. Wonderful. Now, let's look at the total work done. Do we have total work done here? Remember how you get this, right? Total work done is equal to total force applied times the displacement moved from the first point to the final point. So do we have this?
Yes, sir. It's 9.8 times 1,000, I think.
Wrong. Remember, Ft represents a force being applied, right? There is no force being applied here. This moved down the incline, right? Because of this. This wasn't applied. So meaning because there is no, sorry?
I'm saying there is no work done, sir.
Yes, there is no work done, or there is no total work done. Why? Because there is no force applied. No force was applied to move down the incline. It simply moved down the incline as soon as the brakes were released, and it moved down the incline right, based on its components of the weight that is along this axis, which is this one, FG parallel, right? But because there is no force applied, it means this here is 0, right? We have EP1. Remember, 1 and 2 just represents the first and last point, right? Based on which point you are looking at along the object's motion, right? Right now we're looking at the top and the bottom, so this will be 1 and this will be 2, right? So EP at the top we will have a value of, because this is at some height from the ground, right? As far as potential energy, right, EP, remember, is equal to mgh. This h represents h from the point you're looking at to the ground. So for EP1, because this is EP1, it is at some height from the ground. It means you will have potential energy here. Right? Now, what about kinetic energy at this point? Do we have kinetic energy at this point? At the top?
No, sir.
It's a 0.
It's 0 because
For now, it's 0.
it's moving. Yes, this is moving from rest. So at this point, the velocity was equal to 0. Hence, the kinetic energy is equal to 0. Right? Now, as far as the h, let's call it h top. Right? H top. Now, if you look at our incline, it essentially forms a right angle triangle. Are we in agreement here? This is the height you are looking for. Right? So our incline forms somewhat of a right angle triangle. So to get this height, right, we look at the height relative to the angle of incline. So the angle of incline, or the height, is opposite the angle of incline. And this here represents our hypotenuse, which essentially is the distance covered, or the displacement covered, which is 1,000. So bearing that in mind, that the side we're looking for is opposite the angle, the side that we have is essentially a hypotenuse. So using sine theta, h will be equal to the hypotenuse times sine theta. Are we in agreement here? Hello?
Yes, sir.
Yes, sir.
Right. So h top essentially is equal
Yes,
to
sir.
the displacement times sine theta. Right? So we have EP1, it is equal to m times g times h top plus EK1 is equal to 0. So that's 0. Meaning here we can just say this is equal to EP2. What is the potential energy at the bottom?
0, sir.
It's 0.
It's equal to 0. So this will be 0 as well. Right? And then here we are looking for the velocity at the bottom. Right? So we know the kinetic energy is half times m times v at the bottom squared plus Fr times the displacement. Right, now we can substitute. Substituting, the value or the magnitude of m is still m. So this will be m times g 9,8 times h top, which remember is equal to s sine theta. The s is 1,000. Sine theta, theta is 1,146. Right, is equal to half times m magnitude of M is M times V bottom squared plus FR. FR is 0.06 M. So 0.06 M times S, which is 1000. Right. Now, if you look here, each of these terms has M. So essentially M is going to fall away because of that. All of this is going to cancel. And then on the left-hand side, you have 9.8 times 1000 sine 1.146, which is 196.001 368 is equal to 0.5 V bottom squared plus 0.06 times 1000, which is 60. All right, so now you take this to that side. All right, so you're going to get 0.5 V bottom squared is equal to, you're going to have this minus the 60. All right, now you divide both sides by 0.5, and then because we're looking for V, right, we get rid of the square by applying the square roots both sides, and essentially you'll be left with the square root of this here right, and this should give us our velocity. So our velocity is the square root of 196.001.368 minus 60 divided by 0.5, which is 16.493 meters per second. Are we getting the same thing here?
Yes, sir.
Right, that is how you use the law of conservation of energy, people. Any questions?
Sorry, sir. That means if I try to solve it separately, it will not get that answer. Ne?
If you try to,
If I try to solve it step by step by breaking down without putting them together in the same equation.
you're going to get more or less the same thing. So it's not really about the answer. Right? If you follow the right steps,
Oh, okay.
that is what we
Yeah.
look at.
Okay.
Right? But the most important thing here is that as engineering practitioners, right, you must try to be as accurate as possible. Right? That is why, right, in the solution, I try to use as many numbers as possible after the comma for accuracy purposes.
Thank you,
That is just how I prefer doing things. But if you round it off to 3 decimal places, that's still fine. Right? But I would advise, right, to always, while you are still doing the solution, right, to try to use as many numbers after the comma as possible. And then only leave the final answer in 3 decimal places, or round off the final answer to 3 decimal places. Any more questions here? No questions. Wonderful.
Sorry, sir.
Uh-huh.
It's not a question. I just wanted you to please go back to the 2 equations.
Which one?
The equations of law of conservation of energy. Oh, yes, that. Oh, okay, sure. Thank you.
I need to do this one. Right. Can we continue?
Yes, sir.
Right. Let's look at this next one. A motor car of 1,200 kgs is at rest at the top of a 15-meter frictionless slope of 28 degrees to the ground. The brakes of the motor car loosened. It slides on its own down the hill to the bottom and immediately moves onto the horizontal road on its own until it comes to rest after 20 meters. Determine that. All right. All right, so first things first, free body diagram. All right, so we have a motor car. It is at rest at the top of the hill. Okay. Okay. So we have an angle theta here, which is 28 degrees. And of course, you have your normal force. You have the components of the weight. That's perpendicular to the plane. Let's make this orange. So you have FG perpendicular, it's mg cos theta. And then of course we have the components of the weights that's parallel to the plane. That is FG parallel, which is mg sine theta. right? Before there is any force applied, these are the forces that this object is being subjected to. Right. Now let's look at other forces that are at play here. Motor car of 1,200 kgs is at rest at the top of this, frictionless. Right. So because this is frictionless, it means Fr is equal to 0. Right. We don't have to worry about friction. The surface is frictionless. Slope is this. And the brakes of the motor car loosened, it slides down on its own. Right. So there is no force applied here. Right. The object simply moves down the slope on its own as soon as the brakes are loosened. Right. And immediately moves onto a horizontal road. So there is a horizontal road here. Horizontal road. So this here is the horizontal road. Right. Moves onto horizontal road on its own until it comes to rest after 20 meters. Right. So these are all the forces essentially that this object is being subjected to, which suggest, okay, I forgot one thing here, the acceleration, direction of acceleration. Acceleration is in that direction. Now, what does this tell us concerning or regarding Fnet? What is Fnet equal to here? What is Fnet equal to, people?
FA plus FG of parallel.
So Fnet is equal to FG parallel. Right, the vector sum of forces here, the only force along the axis where the work done is taking place is FG parallel. That means the vector sum of forces Fnet is equal to FG parallel. Now it's positive FG parallel because the direction of FG parallel is going in the same direction as acceleration. All right, so the vector sum of forces here is equal to just FG parallel. Now let us look at what else we've been given. The mass of the object, which is 1,200 kgs. Right, is addressed at the top of a 15-meter frictionless slope. So the distance, let's say displacement from top to bottom is equal to 15 meters. All right, they say that at the top of a 15 meters frictionless slope. So the slope is frictionless and is 15 meters long. Right? And then you have theta, which is 28 degrees. And the brakes, okay. And then we are given, so that's all the information we've been given. Okay, I'm lying. We also have the initial velocity on the slope, which is 0 meters per second, seeing that they told us that this is moving from rest. So the initial velocity at the top is essentially 0 meters per second. Right, the final velocity or the velocity at the bottom of the slope we haven't been given. Right, and then they give us moves onto the horizontal road on its own until it comes to rest. So the final velocity on the horizontal road is equal to 0 meters per second, right? When this moves onto the horizontal road, it moves in this direction until it comes to rest. So meaning that the final velocity of the object on the horizontal road is equal to 0. Are we together here? Hello?
Yes, sir.
Right? And it comes to rest after 20 meters. So we are also given the displacement on the horizontal road, which is 20 meters per second. So that's all the information we've been given. Right?
Sorry, sir.
Uh-huh.
Does that mean the final velocity of the slope equals to the initial velocity of the horizontal road?
Yes. So final velocity
Okay.
of the slope is equal to the initial velocity on the horizontal road. That is correct. So that is to say that the velocity at the bottom of the slope is equal to the initial velocity on the horizontal road. That is correct. Very good. That is correct. Right. Determine the following. The potential energy of the motor car at the top of the slope. This here is the top of the slope. Right. This is obviously at some height h from the ground, meaning that we do have potential energy at the top. Right. And just like in the scenario we just looked at, how we calculate the h, right? So h top is still going to be equal to, so h top is still going to be equal to s times sine theta, right? Now s, we wrote here the displacement from the top to the bottom is 15 meters. That is the displacement of the slope, which is the hypotenuse, if you are going to look at the slope from the perspective of it being a right angle triangle. All right, so the slope is 15. So this is 15 sine theta. Theta is 28 degrees. And what is this equal to? So 15 sine 28 is
7.042.
7.04207 meters. All right, they're looking for the potential energy at the top. EP at the top is equal to M times G times H top. All right, so this will be equal to, the mass is 1,200. G is constant, 9.8. H top. So here, I actually prefer using the 15 sine 28. But you could also just use this exactly as it is. What do we get here? So 1,200 times 9.8 times 15 sine 28. So I am getting here 82814,784 joules. You should get more or less the same thing here. Are we getting the same thing?
Yes, sir.
All right.
Yes, sir.
Right, let's look at 4.2. 4.2. Determine the velocity of the motor car after it has moved 8 meters down the slope. Use the applications of the conservation of energy for this calculation. Right? Now, because they've specified which approach to take, right, that means for number 4.2 in particular, you can only use that approach. Right? So they want us to calculate the velocity of the motor car after it has moved 8 meters down the slope. Now we know that the entire slope is 15 meters, right? From the top to the bottom is 15 meters. They want us to calculate the velocity of the motor car when it has just moved by 8 meters, so somewhere here. Right? When this has just moved from the top to say 8 meters, they want us to calculate the velocity at that point when the motor car is moved 8 meters. Right? Using the conservation of energy. Right? Now, using the conservation of energy, this is accelerating. So total work done plus EP at the first point plus EK at the first point is equal to EP at the second point plus EK at the second point plus the work done to overcome frictional resistance. Right? So EP1 is EP at the top, EP2 and EK2 or 0.2 is 8 meters down the slope. Now, do we have total work done here?
I believe we do so.
Now, as per your free body diagram, there is no FT here. FT is 0. If FT is 0, it means WT is 0 as well. You only get this if there is a force applied. Do you get what I'm saying here?
Yes, sir.
Right? Total work done is the work done we get due to the force being applied. So because there is no force that was applied here, it means there is no total work done. Are we together here? Very important you understand this part. Otherwise, you're going to keep making the same mistake here. Right? With work done, each work done is due to the force that induces that work done. And the total work done is induced by a force being applied, which is the total force applied. So WT is equal to FT times S. Similarly with the frictional resistance, work done to overcome friction is equal to FR times S. You only get this if you have this. You only get this if you have this. Now, do we have this here? Is there a total force being applied here?
No, sir.
No,
Because we do not have this, it means we do not have this. Are we clear here?
Yes, sir.
Yes, sir.
Right, so total work done, we do not have. EP1, that is EP at the top, right? Because this point is at some height h, it means we have EP at that point. EK1, what is it equal to? That is the kinetic energy at the top.
0.
0.
So that's 0. EP, now this one, because remember EP2, we are looking at some points. So if we are going to be technical about this, let's do it like, okay. Okay. Right. So we're looking for, this is the first point, this here is the second point. Right. So this point is the second point. Right. Now, obviously, if you look at this point, right, the motor car will be at some height, h, meaning that we will have some potential energy at this point. Right. That potential energy will be based on this height. Let's call this H2. Right. Now, what is H2 equal to here? I just want you to think about it quickly and tell me what H2 is equal to.
So isn't that
It's going to be 7 sine theta.
100%. Right. We applied the very same reasoning we applied to get H top. Right. By identifying that this here is essentially a right angle triangle, the side we're looking for is opposite the angle. From here to here is the hypotenuse. So you use sine. Right. We know from here to this point is 8 meters. Right. So 15 minus the 8 gives us what is left here, which is 7. So meaning this will be 7 sine theta. It is correct. Right. So to get the potential energy at point 2, this is the height we use, which is 7 sine theta. Right. So that is to say we do have some potential energy at point 2. Right. And then kinetic energy, essentially, this is the velocity we're looking for, the velocity that causes this kinetic energy. So the velocity that is built up from the top to after the object has moved 8 meters. That's the velocity we're looking for. And then this, do we have the work done to overcome friction?
it is 0, sir?
It is 0. Why? Because FR is also equal to 0. So essentially we don't have that. So here EP1 is M times G times H top is equal to mass times G times H2 plus half times M times V2 squared. Right, now you substitute. Right, in substituting, now remember that this represents H top, EP top, which we've already calculated. Right, so in fact here, we didn't need to do this. We just needed to realize that the EP1 represents EP top, which we've already calculated. So we could have just said here, this is actually EP top. Right? And then in the next step, you simply just substitute. We already have the value of EP at the top is equal to, the mass is 1,200. So that's 1,200 times G, 9.8. H2 is that 7 sine theta. Theta here is 20 degrees. Right? Plus 0.5 times 1,200 times V2 squared. Right? Obviously, this is what you're looking for. So you take this term to the other side, of which will be left with half of 1,200. What is that equal to? What is half of 1,200, people?
600.
So this is 600 V2 squared is equal to This remains as it is, minus this term. Right? And then, of course, we are looking for V. So we get rid of 600 and the square. By getting rid of that, we get the square root of this of course, divided by the 600. And this should give us a V2. So the square root of 82814,784 minus 1,200 times 9,8 times 7 sine 28. All of this divided by 600, which is 8,580 meters per second. Are we getting the same thing?
Yes, sir.
Yes, sir.
Right. And that is how you would calculate, right, V2 using the law of conservation of energy. Right. This is actually a very convenient formula for us. Very convenient, because the approach of using energy is convenient because you never have to worry about direction. But remember that energy is a scalar quantity. Right? It's a scalar quantity, hence we do not consider direction. That is why even with G here, we don't even think about if G is negative or positive. Why? Because we are using the law of conservation of energy. When you're using any approach that's based on energy, we do not consider direction. Are we clear here? Why? Because energy is a scalar quantity. Are we clear?
Yes, sir.
Yes, sir.
Yes, sir.
Right. That's V2. Right. Now let's look at 4.3. Calculate the deceleration of the motor car on the horizontal road. Right. So obviously, when the motor car gets onto the horizontal road, right, there is no force that is being applied. Hence, the object, after a while, it begins decelerating and eventually stops on its own. So they want us to calculate the deceleration of the motor car on the horizontal road. Now, what do we have on the horizontal road? Which quantities do we have on the horizontal road? Right.
Initial velocity, sure.
We have, so the initial velocity we do not have at the moment, because we haven't calculated the final velocity or the velocity, or have we calculated the velocity at the bottom? No, we haven't. So we do not have the velocity of the motor car at the bottom of the slope. Hence, we do not have the initial velocity, right, on the horizontal road. But what we do have is the final velocity. We know that this comes to rest, so we have the final velocity, and we have the displacement, right, from here to when the car stops. The car moves for about 20 meters. Right, so we only have the final velocity and the displacement, right, which isn't enough to get what we are looking for. right? So the approach here is pretty straightforward. We first need to get the what's this thing? The final velocity, or the velocity at the bottom of the slope, which will inadvertently give us the initial velocity on the horizontal road. Are we in agreement here?
Yes.
Yes, sir.
Right. Now, there are a number of ways in which you can do this. This is 4.3. There are a number of ways in which we can do this, right? One of which is you can use, okay, the easiest one is using the conservation of energy, right? That's the easiest one. Another one that you can use is, of course, by first calculating acceleration and then calculating the velocity using kinematic equations. Right? The easiest one, though, is using the law of conservation of energy, right? Now, first, let us take this step, right? I am taking this step just so you understand where the formula we are going to use, where it comes from, that it comes from the conservation of energy. Right, now we already know that we don't have this. EK at the top is 0. Now EP at the bottom is what? Is also 0. Right, we don't have this. Why? Because there is no friction, so no work done goes towards overcoming friction. So essentially, using the law of conservation of energy, right, EP1, which is EP at the top, is equal to the kinetic energy. EK2 in this case is now EK at the bottom. Do you see what I mean? Yeah? Do you understand where this comes from?
Yes,
Okay.
sir.
Yes, sir.
Right. Now, you have two options here. Because this you've already calculated, you can substitute your EP at the top, and then say this is equal to times m times velocity at the bottom squared. All right, so substitute your EP at the top because you've already calculated it. Substitute the mass here and solve for V. You can take that approach, right? Or you can realize that, remember that EP at the top is equal to the mass times G times H at the top is equal to half times m times the velocity at the bottom squared, right? The mass is going to be the same. To get rid of half, you simply multiply both sides by 2, right? And then this cancels that. And then, of course, getting rid of the squared, it means V bottom will be equal to the square root of 2 times G times H top. Right? So meaningly, instead of doing all this, you realize that because there is no friction or there is no work done due to friction, essentially the motor car is free falling. When the object you're looking at is free falling, this is the formula you can use. Right? But it only works if the object is free falling. Right? The object we're looking at is essentially free falling because it is moving along a frictionless surface. So we can take it as free falling. So only when the object is free falling can we use this formula here. So instead of writing that whole story, you can simply say velocity at the bottom of the slope is equal to this here. The square root of 2g times h top. Right? And you understand where this comes from. Now, are we together here?
Yes, sir.
Yes, sir.
Right? So this is a much quicker approach as opposed to having to first calculate acceleration and then using kinematic equations to calculate the velocity at the bottom. So now all you do here is substitute. So that's 2, 9,8. H top was 15 sine 28. All right, so square root of 2 times 9,8 times 15 sine 28, which is 11,748,484 meters per second. That's the velocity of the object at the bottom of the slope, which means the initial velocity on the horizontal road is equal to 11,7484 meters per second. Right, now we have enough information to calculate the deceleration because we have the initial, we have the final velocity, and we also have the displacement. Right, so using this kinematic equation, final velocity on the horizontal road is equal to the initial velocity on the horizontal road. Right, this is decelerating, so minus 2a displacement on the horizontal road. And then a will be equal to initial minus final divided by 2s. Right, initial is 11,7484 squared minus 0 squared divided by 2 times s. Now the s on the horizontal road is 20 meters. So that's 20. So 11,7484 squared minus 0 divided by 2 times 20. I am getting here 3,451 meters per second every second. Are we getting the same thing here?
Yes, sir.
Yes, sir.
Right, very easy. I prefer this approach. Now, this is just on a personal note. I prefer this approach because it helps in me getting the magnitude of the deceleration as positive. That way I don't have to confuse having to use it as positive or negative if ever I have to use it again in calculating the vector sum of forces. All right, so I would advise that you use this approach as well, seeing that the direction of the forces we look at in relation to the direction of acceleration. Any questions? Very, very, very easy stuff. As long as you understand the concepts that we use in dynamics, it becomes very easy. Also, doing everything in relation to the free body diagram makes things easy, easy, easy. When I talk about free marks, these are free marks here. 4.4, kinetic energy after moving 20 meters on the horizontal road. Easy one. What is that equal to?
0.
Yes. Final velocity is equal to 0. That means the kinetic energy, right, after 20 meters is equal to 0. Very easy. Any questions? No questions. Wonderful. Right. As far as dynamics, essentially we've covered everything, I believe. The problems we have done here essentially covers everything. Even what I didn't cover in the videos I uploaded on my channel, which is the law of conservation of energy. Now you know how to express the law of conservation of energy mathematically and how to use it in calculating whichever quantity you might be looking for. Right, we were going to do one more, but this one I will give you for you guys to do on your own. When I send the work we did today, I'm going to include it here, and you can attempt it on your own. Right, I'll share the solution either tomorrow or Saturday. In fact, I'll share the solution as well, but just attempt it on your own. And then you can use my solution, right, to gauge if you did everything accordingly. And then if maybe you messed up somewhere, so you can check where you messed up. I don't think people will mess up though. Is that a correct assumption?
Yes.
Right, any more questions on dynamics? No question on dynamics. So no questions on dynamics, no? Are we still here?
Yes, sir.
Yes, sir.
Yes, yes.
All right. So if there are no more questions on dynamics, that's pretty much it for this evening, as far as dynamics. All right, so we can move on to hydraulic presses. Perhaps let me give you, say, 2 minutes to stretch, drink some water, maybe hit the head if you need to. But I'll be giving you, okay, let's say 5 minutes. Do you need the 5 minutes? Or can we continue?
Please give us the 5 minutes, sir.
All right. So I'll give you 5 minutes. We'll continue at 1950. Right. I'm not going to end the session here, though. Right. We'll just wait. Right. I'll then speak at around 1950. Make it 1951. Yeah. Hello. Are we back?
Yes, sir, I'm in.
What about everyone else? He said 5 minutes, people.
Yes, sir, we're back.
Yeah.
All right. You guys can still see my shared screen, right?
Yes, sir.
All right. Okay, now we're going to look at problems based on hydraulic presses. Right?
Yes, sir.
Your assessment only includes the hydraulic presses part of hydraulic systems or hydraulics. Right, so it is to say that hydraulic pumps, hydraulic accumulators are not included in the assessment because of time. But there wasn't enough time for you guys, or the way I look at it is there wasn't enough time for you guys to look at hydraulics in its entirety. Hence, I only included hydraulic presses. Right? But we are going to address any lingering questions on hydraulic pumps and hydraulic accumulators, but after the assessment. And so right now, you can just focus on what is included in the test. So the topics included in the second assessment. Right, let us look at this problem, 6.3. It's based on hydraulic presses. Hydraulic press has a ram diameter of 85 millimeters. So just like with every topic, it's very important that you write down the information we've been given. Right, they said the hydraulic press has a ram diameter. So we have DR. DR stands for diameter of the ram, which is 85 millimeters. Convert that to meters and you get 0.85 meters. The plunger diameter, that one is denoted as DP for diameter of plunger, is 15 millimeters, which converted to meters is 0.015 meters. With a stroke length, that's SL, 30 millimeters, which is 0.03 meters. The mechanical advantage on the lever, that's the mechanical advantage on the lever. So the mechanical advantage that they've given us is for the lever system. Remember that a hydraulic press, right, is a system that composes of essentially two systems, the hydraulic press itself, and it works in conjunction with a lever system. Right, so essentially, you get the mechanical advantage of the lever system, and you get the mechanical advantage of the hydraulic press. So here they've specified that this mechanical advantage is for the lever system. So you have mechanical advantage MA of the lever system. So the L stands for lever system, which is 11. Right, calculate the following. So 6.3.1, calculate the force needed to lift a mass of 3.5 tons. So now they've also given us the mass that has to be lifted. It is 3.5 tons, right? The tons you have to convert to kilograms. Hence, converting 3.5 tons to kilograms, you will get 3,500 kilograms. If the efficiency, so you've been given the efficiency is 75%, which is 0.75. Right, calculate the force needed to lift a mass of 3.5 tons if the efficiency is 75%. Right, now, they said the force needed to lift a mass of 3.5 tons if the efficiency is 75%. right? If they've asked you to calculate a force needed to lift a mass, if the efficiency is 75%, essentially what they want you to calculate, right, will be based on if you've been given the mechanical advantage, right? If you've been given the mechanical advantage, that suggests that the force that they are looking for is actually the effort. What is this thing? Let's just call it E, the effort. Right, so because we've been given the mechanical advantage of the lever system, it means, or that suggests that the force that they're looking for is actually the effort. Right, if you think of the video I uploaded on hydraulic systems, on hydraulic presses, where I explain how a hydraulic press works essentially. Right, the only formula that we get on the lever system is the one based on mechanical advantage. Right, remember that on the lever system, you get the effort. That effort is multiplied by the mechanical advantage of the lever system, which gives us the force coming out of the lever system, which is force on the plunger. Right, so manipulating this formula, making MA the subject, essentially MA, which is the mechanical advantage of the lever system, is going to be equal to FP divided by the effort. This is the only formula that we have on the lever system, or that we can use on the lever system. Right, so that is to say that if you've been given the mechanical advantage, right, even if they haven't specified that the mechanical advantage is for the lever system, even if they haven't specified if it's for the lever system or if it's for the hydraulic press, if they haven't specified, then you always assume it's for the lever system. Why? Because we can only use this formula in the lever system. Right? If you haven't been given the mechanical advantage of the lever system, it means essentially they won't require you to calculate the effort, because the only way to calculate the effort is through the use of this formula. Right? So that is to say here, as much as they didn't tell us, or as much as they didn't say calculate the effort, the fact that they said calculate the force needed to lift, and they've also given us the mechanical advantage, that suggests that they're looking for the effort. Now, typically, they would tell you to calculate the effort. But if they haven't, and they've asked you to calculate the force, and you've been given the mechanical advantage, then you assume that they are looking for the effort. Are we clear? Hello?
Yes, sir. We clear, sir.
Right. So bearing in mind that you are looking for the effort, right? We know to get the effort, you need the mechanical advantage, which we have, and then you also need the force on the plunger, right? Which at this point we do not have, but we can get it, right, using Pascal's law, right? Using Pascal's law. So first, we've been given the mass of the object that has to be lifted, right? We do know that Fr, right, is equal to the weight of the object being lifted. The weight of that object is equal to m times g. The mass here is 3,500. G is 9.8. And what is this equal to? So 3,500 times 9.8 is 34,300 newtons. Are we getting the same thing here?
Yes, sir.
All right. Once you have FR, now we can use Pascal's law to calculate FP. All right, using Pascal's law. Now remember here we have efficiency. All right, the hydraulic press. Right, isn't 100% efficient. Now, before we continue, they haven't specified here if it's the hydraulic press or the lever system that is not efficient. Right, so we are going to look at two approaches where we assume it's the hydraulic press that isn't efficient. And then for our alternative solution, we are going to assume that it's the lever system that isn't efficient, or that is 75% efficient, and see if we get the same effort. Right. So assuming that the efficiency is for the hydraulic press, using
Excuse me, sir.
Pascal's law. Yes.
Can I just ask something quickly? So now they don't specify where the efficiency is. Do we do both of them? Apply it to the plunger and the ram, or only or what do we do in this situation now?
You use it
Say
for
what they give like that in the exams. Do we apply that efficiency to the ram or the plunger?
you apply. So you choose. You either apply or you either assume that the efficiency is for the hydraulic press, or you assume it's for the lever system. You must choose one, because you cannot use this twice. That is why we are going to use essentially two alternatives. So the first alternative, we are going to assume that this here is for the hydraulic press. The second alternative, we are going to assume that this is for the lever system. You should get the same thing either way. So that is to say that you use either or, use one of them.
Okay, thank you.
Right, so using Pascal's law, right, we are assuming that the hydraulic press is the one that isn't 100% efficient. So we say here, efficiency times force on the plunger divided by the area of the plunger, which is pi over 4 times dp squared is equal to force on ram divided by area of the ram. At this point, I'm thinking I don't have to explain where this comes from, right? Because people have went through the content. Hello.
Yes, sir.
Yes.
Yes, sir.
Right.
Sir.
Correct.
Now, the power of 4 is the same both sides, so that cancels. Right, and this is what you're left with. Remember here, we want to calculate or want to determine FP. Right, so making FP the subject of the formula here, right, this will be equal to FR times dp squared divided by the efficiency times dr squared. Now you substitute FR, we got 34,300. dp is 0,015 squared divided by the efficiency, which is 0,75 times dr, which is 0,085 squared. right? And this will give us our FP. So 34,300 times 0.015 squared divided by 75% times 0.085 squared. So I'm getting here 1424,22145 newtons. Getting the same thing here. Hello. Are we getting the same thing?
Yes, sir. Same thing.
Right. So once you have your FP, remember at this point, you had already established that this is what you're looking for, but to get this, you need this and that. So meaning now you can calculate your effort. All right, calculating your effort, we know mechanical advantage is equal to F out, which is FP, divided by the input force, which is the effort. This is on the lever system. And then to get E, you simply manipulate this formula, which will now be FP divided by the mechanical advantage, the lever system. Right, FP, we calculated, and this is what we got. This divided by the mechanical advantage, which is 11. And this gives us, so this gives us 129,475 newtons. Are we getting the same thing?
Same answer.
Yes, sir.
Right, so if we assume that the efficiency that we've been given is for the hydraulic press, this is the approach you would take, and the effort will be equal to this here. Okay, let's do this. Let's say, assuming hydraulic press is 75% efficient. That is the approach. Let's say, or now we are assuming lever system is 75% efficient. Right. So now it's not the hydraulic press. That is 75% efficient, but it's the lever system. So in using Pascal's law, because we are still going to need FR. So you calculate your FR. So FR is equal to the weight of the object being lifted. That is equal to mass times G. Mass is 3,500. G 9,8. You get 34,300. And then applying Pascal's law, FP divided by dP squared is equal to FR divided by dr squared. And then you make FP the subject. So FP will be equal to FR times dP squared divided by dr squared. FR is 34,300 newtons. dP is 0.015 squared divided by dr, which is 0.085 squared. And this gives us the force on the plunger. So 34,300 times 0.015 squared divided by 0.085 squared. So I'm getting here 1068,16609 newtons. Same.
Same.
Right. Now you have FP. So to calculate the effort, right, we know that this is the only formula we can use on the lever system. The mechanical advantage on the lever system is equal to the output force on the lever system, which is the force on the plunger, divided by the effort, and you multiply this now with the efficiency. Your input force on the lever system. Then from here, you then solve for E, which is the effort. So the effort is equal to FP divided by mechanical advantage of the lever system times the efficiency. Right, so this will be equal to FP, which is this, all of this divided by mechanical advantage, which is 11, efficiency, which is 0.75. So this divided by 11 times 0.75 is 129,475 newtons, which is the same thing we got when we assumed that the efficiency is for the hydraulic press. Any questions? So the most important thing here is realizing that if they haven't specified which system between the lever system and hydraulic press the efficiency is for, then you can use any one of these approaches. Either way, you are going to get the same magnitude for the effort. Right. That is to say, the efficiency of either system only influences force on the plunger. Are we clear?
Yes,
Clear.
sir. Clear.
Right, can we continue?
Yes, sir.
Right, so that was 6.3.1, 6.3.2. Calculate the number of strokes needed to lift the load 150 millimeters if there is a slip of 6%. 6.3.2. Let's see what you've been given here. They want us to calculate N. Number of strokes is N needed to lift the load. So we've been given the height lifted. Height lifted is 0.15 meters. If there is a slip of 6%. So there's a slip of 6%. All right. So this is what essentially we've been given on 6.3.2. They want us to calculate the number of strokes. They gave us the heights lifted as well as the slip. All right. Now this here, slip. Right. When you convert slip into efficiency, the thing to understand there is that the efficiency you get, or the efficiency due to slip, alludes to the hydraulic system's, what is this? Volumetric efficiency. Right, it alludes to the hydraulic system's volumetric efficiency. Right, which will be the 100 minus the slip. So to get that efficiency, right, it's 100 minus slip. So that's 100 minus 6, which is 94%. Right, so that is to say that the efficiency we get due to slip is referred to as, or is referred to, as the volumetric efficiency. Now, volumetric efficiency, the understanding around volumetric efficiency is actually that, so this you are going to use a lot when it comes to hydraulic pumps, right? But the understanding is the same. Volumetric efficiency alludes to the hydraulic systems, what is this? Efficiency when it comes to the discharge, right, of the fluid that is in the hydraulic system. Right, with hydraulic systems, you get the theoretical discharge, and then you get the actual discharge. Right, this is how we look at it in terms of fluid mechanics. Right, the right way of looking at it. Right, when you look at it from the, from the lens of fluid mechanics, right, volumetric efficiency has to do with this here, the theoretical discharge and actual discharge. Now this, which is the theoretical discharge, you get if the system is 100% efficient. It is called theoretical because that can only happen theoretically. There is no such thing as a 100% efficient hydraulic system. Hence the term theoretical. Right, and then the actual discharge. Right, by discharge, this is what we mean, people. the flow rate, which will be in cubic meters per second, right? And then the theoretical or actual discharge is the actual flow rates that we get in the system when the system is not 100% efficient. Perhaps you have heard of the term coefficient of discharge, right? The coefficient of discharge is actually equal to volumetric efficiency. Right? And CD is equal to actual divided by theoretical. So when you've been given this, it actually alludes to this. That based on this, based on the slip being 6%, it means the volumetric efficiency, which essentially is the coefficient of discharge, is equal to 94% or 0.94. Right, and like I said, the difference essentially between the two, this being theoretical means that the system is 100% efficient, which is theoretical because there is no such thing as a 100% efficient hydraulic system. And this here is the actual, which is why to get the actual, right, you simply cross multiply here. And then in cross multiplying, this will be CD, or volumetric efficiency, times the theoretical velocity, the theoretical discharge, and this will be equal to the actual discharge. Right? So this is through the lens of fluid mechanics, essentially. Now, bringing us down a notch to the lens of engineering science, right? With hydraulic presses, right? The hydraulic press has two sides to it, essentially. You have the side of the plunger piston, and you have the side of the ram piston. And the way it works is that the volume of fluid is displaced from the plunger side of the hydraulic press. As it is displaced, right, that displaced volume of fluid is then received by the ram. Right, so through the lens of engineering science, hydraulic presses, right, instead of just QT, we will have, so this will be CD. Okay, let's call it now the volumetric efficiency times, instead of QT, you have the volume of fluid which is displaced by the plunger is equal to the actual fluid that is received by the ram, which is the volume of fluid received by the ram. Right, so this here essentially comes from understanding this, that when there is slippage, the slippage alludes to the hydraulic system's volumetric efficiency. This is how it is interpreted. And then as far as hydraulic presses, because you don't actually look at the flow rate, instead we look at the volume of the fluid being displaced. So this is how we express it. Right, when the system is 100% efficient, we say this is equal to that. But when the system, just like with this one, is not 100% efficient, that is when we include the efficiency or the volumetric efficiency. So this here represents essentially the theoretical volume of fluid being displaced, and this here represents the actual volume of fluid being received, which will be X times efficiency. Are we clear here?
Clear, sir.
Right, that is where essentially this comes from. Now, in the video I posted on hydraulic presses, right, I explained this at surface level. Right, now you have an actual understanding of where it comes from. Right, and then also this here, this represents the volume of fluid being displaced in one stroke. Right, so the VP, right, this here represents the volume of fluid being displaced, right, per stroke or in one stroke. And then if you're looking at what happens after a certain number of strokes, then this changes to VP, which represents the volume of fluid displaced in one stroke, times the number of strokes that in that scenario you would then be looking at, is equal to the volume of fluid being received by the ram. Right? Remember here, we are looking for number of strokes. The number of strokes it would take, right, for the object to be lifted to a height of, or by a height of 0.15 meters. Right, so this essentially is your formula as far as the volume of fluid being displaced by the plunger being equal to the volume of fluid being received by the ram. All right, now breaking this down further, we would have the efficiency times, and then the volume of fluid being displaced by the ram is actually equal to the area of the plunger times the stroke length. Area of the plunger is pi over 4 times the diameter of the plunger squared. That's the area of the plunger times the stroke length. So this here represents the volume of fluid being displaced by the plunger in one stroke times certain number of strokes is equal to, and then the volume of fluid being received by the ram is equal to the area of the ram, which is pi over 4 times diameter of the ram squared. Right, so this here is the area of the ram times the height lifted. Right, so this gives us the volume of fluid being received by the ram. Right, and then of course here, this and this cancel, and now we can make n the subject of the formula. Right, making n the subject, n will be equal to dr squared times the height lifted divided by the efficiency times dp squared times the stroke length. right? Now you substitute dr here. What is dr equal to here? That's dr is 0.085, 0.085 squared. Height lifted is 0.15 divided by the volumetric efficiency, which is 94%. That's 0.94 times dp, which is 0.015. 0.015 squared, stroke length, which is 0.03. Remember, it's 30 millimeters. Right, so 0.085 squared times 0.15 divided by 0.94 times 0.015 squared times 0.03, which is 170,804. Right, now this here is the number of strokes. Right, so because it is a number of strokes, you have to approximate your answer. Right, we can't say there is 170,804 number of strokes. Right, so you round this off mathematically. So rounding this off mathematically, you then say 171 number of strokes. Any questions? Hello.
No, nothing, sir. Thank you.
Right, so that is how you look at slip, people. Right, if you're looking at hydraulic presses, so specifically for hydraulic presses, well, this is how you look at it. Right, but for hydraulic systems where we consider the flow rate of the fluid being used, right, this is how you look at it. Right, this here is how you look at it. When we discuss hydraulic pumps, right, this is how we are going to be looking at it, right, because for hydraulic pumps, we do consider the flow rate of the fluid in use. Happiness? Hello? Are people still here or are we sleeping? What's going on?
No, we're still alive, sir.
We still alive, so we still good.
All right.
Dead cat, no? You just want to see us dead, you know?
Hmm?
No, sir. Sorry, sir.
All right. Right. Can we continue?
Yes, sir, we can continue.
Right. So let us look at question 5.3 here. 5.1 and 5.2, you should be able to define on your own. Either way, I've included the answers to those two questions. right? That is density, pressure, Pascal's law. Right, so let's just hop onto 5.3. Right, as per the use, you write down your given data. 5.3 reads as follows. The diameter of the ram cylinder of a hydraulic press is 100 millimeters. So we have dr, which is 0.1 meters, stroke length is 40 millimeters, so that's 0.04 meters. Mechanical advantage, MA, is equal to 30 on the plunger. Right. 5.3.1, calculate the volume of liquid needed per stroke if the load has to be lifted 80 millimeters is 50, or so this, I think it was supposed to be in 50 strokes. There is a slip of 5%. Something is missing here. Diameter of the ram, 100, stroke length is this, mechanical advantage is that. Oh, okay. Right, so they want us to calculate the volume of liquid needed per stroke. Right, remember here, I explained, right, what each of these actually means. Right, remember I said that this represents the volume of fluid being displaced by the plunger in one stroke. So when they say calculate the volume of liquid needed per stroke, so they want us to calculate VP here. If the load has to be lifted 80 millimeters in 50 strokes, there is a slip of 5%. So in 5.3.1, we are given additional info. We are given the height being lifted, which is 0.08 meters. Right, we are given N, which is 50 strokes. We are given the slip. So we have the volumetric efficiency of how much? 0.95. We are looking for volume of fluid being displaced in one stroke. Right? So we have volumetric efficiency, meaning this is how our formula is going to be. Efficiency times VP times N is equal to the volume of fluid being received by the ram. Right? This is what we are looking for. So we get rid of this and this, making VP the subject. So this will be equal to VR divided by the efficiency times N. So what is this equal to? VR is equal to the area of the ram, which is pi over 4 times dr squared times the height lifted. Right, this here is what is equal to the volume of fluid being received by the ram. It's the area of the ram times the height lifted. And then, of course, we have this now divided by the efficiency times N. Right, this can also be written as pi, and then you have 4 here. So this is equal to, now you substitute. So this will be pi times, what is dr equal to 0,1, 0,1 squared times height lifted, which is 0,08, all this divided by 4 times efficiency, volumetric efficiency is 0,95 times n, which is, okay, 50. Right, and this will be equal to pi times 0,1 squared times 0.08 divided by 4 times 0.95 times 50. So the volume of fluid being displaced in one stroke is 13,2278 times 10 to the negative 6 cubic meters. Are we getting the same thing here?
So I'm not getting the same thing, so
What are you getting?
I'm getting 1,3227
Times?
times minus, times 10 to the power 6.
Nope. Times 10 to the power 5.
6, sir. Minus 6.
Can't be.
So is it the same thing?
It will only be the same thing once you press engineering notation. Initially, you're going to get 1,322775854 times 10 to the
Yes,
negative.
sir.
And then if you press engineering notation, then you will get 13,227 5854 times 10 to the negative 6. You get what I'm saying?
Okay, sir.
Are you getting the same thing here?
Yes, sir.
Right. So that is our VP. Right. Volume of liquid needed per stroke. This is what they're referring to. It's very easy, straightforward. Right. If you understand what this is and what this is, it is very easy to attempt or to know how to approach this question, because we already know that this here is the volume of fluid being displaced in one stroke. Right. So let's look at now 5.3.2. Calculate the diameter of the plunger. Right. That one is pretty straightforward as well. We know the velocity of fluid being displaced by the plunger is equal to the area of the plunger, which is pi over 4 times dp squared times stroke length. Right. This we've already calculated. This we are given, so we need to solve for that. Right. Making the diameter the subject of the formula here. This will be equal to, let's remember, we are looking for dp, so it means we need to get rid of the pi, the divided by 4, the stroke length, and the square. Right. And then you will get the square root of Vp times 4 divided by pi times stroke length. right? And now you substitute. Right, substituting VP is 13,2278 times 10 to the negative 6 times 4 right, divided by pi times the stroke length, which is 0.04. And this gives us our diameter. Square root of 13,2278 times 10 to the negative 6 times 4 divided by pi times 0.04, which is 20,52 millimeters, or you can say 20,52 times 10 to the negative 3 meters. You guys understand how these answers come about, right?
Yes, sir.
Right, so they haven't specified if we should leave your answers in millimeters or meters. So it doesn't matter how you express it. Right, any questions here?
Oh,
Simple straps. Hydraulic systems, hydraulic presses, very easy. Once you understand, as long as you understand how a hydraulic press works, right, so this is why I recorded that video I uploaded on hydraulic presses. Right, the key to hydraulic presses is understanding how it works. If you understand how it works, the calculation side of things becomes very easy. Right, can we continue? Hello.
Yes, sir.
Yes.
Right. I thought you were sleeping. I haven't heard you in a while. Now, 5.3.3. Calculate the effort required on the bundle to lift a load with a mass of 1,2 megagrams. This one is pretty straightforward. It's not that different from the question we just finished. They want us to calculate the effort. We've been given the mechanical advantage. Now, if you look here, they said the mechanical advantage is 30 on the plunger, which doesn't really specify if it's for the lever system or the hydraulic press. But like I said, because we are only able to use the mechanical advantage on the lever system, if you've been asked to calculate the effort, or if you've been asked to calculate the force required to lift the load, having been given the mechanical advantage, you take it as though that the mechanical advantage you've been given is for the lever system. Are we clear here?
but sir, doesn't it then say there in that question the mechanical advantage is 30 on the plunger and not on the lever?
Remember, the plunger is on both systems, both the hydraulic press and the lever system. Remember that the force on the plunger is the output force on the lever system, but it is the input force on the hydraulic press.
Oh, okay, thank you.
Yes. You see how easy this thing becomes if you understand how a hydraulic press works. If you understand how a hydraulic press works, the calculation side of things, easy peasy. Are we clear?
Yes, sir.
Right. They want us to calculate the effort. The mass is 1,2 megagrams. Mega is the same as ton. Ton is equal to 1,000 kilograms. So 1.2 megagrams is equal to 1,200 kilograms. All right, so this is 5.3.3. All right, you are given the mass of the object being lifted, which is 1,200 kilograms. They want us to calculate the effort. In calculating the effort, we need the mechanical advantage, which we have, it's 30. And we also need force on the plunger, which we do not have, but we can calculate using Pascal's law. So first you calculate Fr, which we know is equal to the weight of the object being lifted. That is equal to M times G. M is 1,200, G 9,8. Right, 1,200 times 9,8 is 11,760 newtons. Right, they said nothing about efficiency, right? Absolutely nothing. So we assume it's 100% efficient. So applying Pascal's law, right, we know FP. Right, so that is Pascal's law essentially means, by applying Pascal's law, we essentially mean that we use the formula, the pressure exerted by the plunger piston being equal to the pressure exerted by the ram piston. Mathematically, it becomes FP, force on plunger, divided by the area, which mathematically would become dP squared is equal to the pressure exerted by the ram, which is Fr, divided by the area, which essentially would become dr squared. Solving for FP, FP will be equal to Fr times dP squared divided by dr squared. Substituting, this is 11,760 times dP, which we calculated, and remember this is what we got. So dP is 20,52 times 10 to the negative 3 squared divided by dr. What is dr? Equal to 0,1. So this is 0,1 squared. So 11,760 times 20,52 times 10 to the negative 3 all squared divided by 0,1 squared. So this becomes 495,178.79 newtons. Are you getting the same thing?
Yes, sir.
Right, that's the force on the plunger. Now to get your effort, we know MA on the lever system is equal to output force, which is the force on the plunger, divided by the input, which is the effort. Therefore, meaning the effort is equal to force on plunger divided by mechanical advantage of the lever system. Now you substitute, FP is what we got here, divided by mechanical advantage, which was 30. All right, so this divided by 30 gives us 16,506 newtons. Any questions?
No, sir.
All right, so 5.3, that is it. Happiness?
Sorry, sir. Can I see that 5.3 again, sir, please?
The question,
No, the answers.
which one?
5.3. 33. The last one. Okay, thank you, sir.
Any more questions? So this one, we aren't necessarily going to do. I just want to emphasize how we interpret this information here. When you haven't been given either of the diameters, be it the diameter of the ram or diameter of the plunger piston, when instead they've given you somewhat of a relationship between the two of them, how you go about approaching such a question. Can we continue?
Yes, sir.
Right, so here they said the diameter of a ram so dr, they said the diameter of the ram is thrice that of the plunger. So mathematically, that means dr is 3 times dp. Right, so I want us to look at how you use this relationship when you haven't been given this or that, but instead you are given somewhat of a relationship between the two. Because if you look at the question, they want you to calculate the effort, calculate the force needed to be applied by the lever or handle. That is the effort. You already know how to calculate the effort, even when either of the system or one of the systems, be it the lever system or hydraulic press, is not 100% efficient. Right? At this point, you know how to do that. I just want to show you how you use this information. Right? We know in calculating the effort, you need the mechanical advantage, which you do have, as well as the force on the plunger. Right? And in calculating the force on the plunger, you simply apply Pascal's law. Right? So depending on the approach, say your approach is such that you assume that it's the hydraulic press that is 91% efficient. That will mean in calculating the force on the plunger, this will be your approach, divided by dp squared is equal to Fr divided by dr squared. And then in calculating Fp, or in making Fp the subject of the formula, you will have Fr times dp squared divided by the efficiency times dr squared. And then when you substitute at that point, you would have already calculated Fr. They've given you the mass here, the mass of the object being lifted. So you can get Fr times, we do not have the value of dp, so you leave that exactly as it is. Here you substitute the value of the efficiency times, and then dr, as much as you don't have a value for dr, but you know dr is equal to 3 times dp squared, I mean dp. So here you have dp squared, right? And then this will be Fr times dp squared divided by the efficiency times, now this here, 3 squared is 9, and then dp squared is dp squared. And then of course, this and that cancels. And essentially, you'd be left with Fr divided by the efficiency times 9. Do you get my point?
Yes, sir.
Right, that is how you use this relationship. Essentially, the two are going to cancel each other out. Are we clear?
Clear.
Yes,
Yes,
sir.
sir, we clear.
Right. Let's look at one more that includes work done.
So you cancelled that one before I could even take a screenshot of that one actually.
I will send it to the group. Do not worry, Chief.
Sure.
I'll send it to the group. Don't worry. Right. Now with this one, we already know how to calculate the effort. We know how to calculate the number of strokes. This is the only part we haven't really done here, how to calculate work done. Right. Now we know work done in general is equal to force times displacement. Right. Now, when calculating the work done by the plunger, right, you of course have to use the force on the plunger, right, times the displacement of the plunger. Now, as far as the displacement, it's going to be the stroke length times, of course, the number of strokes. So this is how you calculate the work done by the plunger. And then the work done by the ram, it's force on the ram times the height lifted. So the displacement, as far as the ram piston, we refer to it as the height lifted. Now, if you look at this question 5.2.3, right, it says calculate the work done by the press in kilojoules to lift the load 110 millimeters. Right, so seeing that you are given the height lifted, you're simply going to use this here. Work done by ram, you have the height lifted, right? And they've given you the mass of the objects being lifted. Hence, you are able to get FR. So you substitute those two here, you get your work done by the RAM, making sure that you convert what you get to kilojoules as per the instruction here. Are we clear here?
Yes, sir.
Yes, sir.
Right. We'll send all of this in the group. Right. But as far as hydraulic presses, we are done. Any questions? No questions.
I'm good, sir. Thank you.
Alrighty then. The session was 3 hours. Proper 3 hours. I'm happy with the work we're able to do during this session. Right, if there is absolutely nothing else, I think we can call it a day.